Okay, great welcome to all of you that you are here to hear about Akka.JS and why vector model matters, even on the JavaScript world. Will be crazy, but you will see what happened. So, first of all, who am I? I'm Andrea Peruffo, and right now I'm working for Nokia. I'm a 10+ year software developer. Right now I'm doing mostly DevOps, but I developed in a number of fields from embedded system, PLCs, FPGAs, cloud system, big data, whatever. Right now DevOps on big data, whatever. And so many different things. I started as a Java fellow many years ago, and then a long time with Scala, actually. And this is me, and my handles are Andrea TP on GitHub and AndPRF, so feel free to reach me. Digital messages are open on Twitter. And yes, this is my dog, Guido. And so let's start from the theory. We are going to talk about the actor model. What is an actor? An actor is, we start from the very definition that is back in '73. And an actor is an execution unit that can run concurrently with other actors. So this is the very basic definition. We will start from really simple concept and a few, but this is the very foundational one. And it can communicate with other actors through message passing. This is incredibly important. So actors live in a world, and they can communicate through message passing, just sending a message to others. It can change his behavior. So while he receives a message, he can change what he will do next time. So this is a basic foundation. And it can spawn other actors. So new actors can come from one. And these are the very only three attribute that an actor has. So this is the very foundation of what we will do and we will see all today, and we want to elaborate on this. What is happening nowadays? We have a number of languages, libraries, and whatever that are implementing vector model. There is already Erlang, Akka, a number of libraries, and rolling drums, and all of them are implemented based on the foundation that we just seen. Why? Because it's arguably good model to handle concurrency. We have seen the word concurrency in the very definition of vectors, and all these libraries are really good in managing concurrency. What comes from the definitions and the attributes enable the vector model to be a really good solution for managing even parallelism, because this becomes transparent for the end user. And then we have a number of features that we can implement on top of it, that is location transparency, distribution, high availability, fault tolerance. All of this framework, all of these languages are implementing such features and are pushing these limits to enable distributed system, especially in the cloud, but even in IoT and in a number of fields to scale up and scale out on machines and build a new distributed system. But yeah, why? And the answer is simplicity. So we are removing all the complexity. We are removing all the tricky things to do. The key thing is that we have a really simple model where actors can talk to each other just through message passing. We eliminate concurrent data structure. We eliminate synchronous things. We eliminate everything that is hard to manage, mutex. We eliminate synchronized. We eliminate all the things that are really hard to handle in concurrent and parallel programming in nowadays informatics. Simply changing the point of view. So vector models say that everything is asynchronous. Basing everything on this basic concept, all the rest becomes for free. And all the rest is handled by the framework itself and no more by us. And yeah, we are talking about JavaScript, and you can say that we don't have this problem in JavaScript, but as they already said, there are many things that are coming with new specification of JavaScript. Are you sure that you don't have? There are workers that are shared workers, shared array buffer, whatever. So even JavaScript is becoming real multi-thread. A little bit of context here, and what I will show you comes all from this library that is Akka. Akka is an actor framework written originally in Scala, but has also a really nice Java API for you Java fellows. And it's a really great library. It's huge. It covers many aspects and a lot of functionalities of actor system. Today we will see only really few things, very basics, but Akka is full-featured, enterprise used, really a great library. And it happened to be written in Scala. And on this slide, we can say that there is an alternative Scala compiler that is called the Scala.JS. And basically, you can compile your Scala code instead of bytecode to JavaScript directly. Scala.js is an amazing project, is incredibly stable. It is going to become version 1.0, but it is already stable since years. And the developer of Scala.js is a great guy and is a really great project. I put the two things, yes, trivial, right? take one JVM library for actor model, take a compiler that compiles Scala to JavaScript, and there is Akka.JS. Since a few months ago, a couple of months ago, all of this was available only for Scala developer to be used from Scala.js, and here I am to present it to you, the JavaScript bindings. So finally, it is available also for JavaScript developers that, without knowing anything about Scala, can simply use vector model from JavaScript, from pure JavaScript code. And why you should care about Akka.js? You have many things that are going on. Async await promises are great things for handling concurrency on JavaScript. Yeah, but I think we can do better. And I want to stop now talking about theoretic things. And we want to go through a really pragmatic proof of concept. And we want to implement something, an exercise. Now, let's do an exercise with Akka.js. Let's see how it looks like and how it feels to develop an application with it. We want to build a full stack proof of concept for a Twitter streaming service. So we will have a backend written on top of Node that we will stream Twitter messages onto our front end that will show you the result. Let's see. First of all, the backend. We have Akka.js, of course, and Akka.js, as I have said, it's available as an npm package. It's incredibly easy to use and incredibly easy to get started, of course, as any other npm package. So you have examples, you have a full API described. It is not really complete as Akka is, but new features just need to expose an interface. So it will be really easy in the future to add functionalities without having to really implement them, just adding an API that is familiar for JavaScript developers. And we will base everything on it. Our backend architecture will involve a WebSocket server. So we will spawn an actor that will be a server that is able to handle connection. So every connection will be handled by an actor that will be the WebSocket server. Then we have a WebSocket channel. This is extremely easy to think actor-wise. Every time we receive a connection, we simply spawn a new actor that will handle this connection. So for every client that will connect to our server, we can simply reduce our problem to have it in a one-to-one problem. So each channel will be mapped to one client, and it will be an actor. Easy peasy. And a Twitter server, so this channel will simply spawn a Twitter service that will connect to Twitter to stream things through the WebSocket. I'm not a Node developer, so what I have to do, I was told that for NPM there is anything, and I write Node WebSocket, and there is a fantastic library, WebSocket called. That is great. I just scroll down until the example, and I start to implement it. Our server is a Java. We are talking about JavaScript, of course. I think I can increment a bit the font. Our web server actor will be an actor, of course, and it will be constructed using a port. I'm sorry, I'm using class, and I'm using them like real class and objects. But and we have 3 methods that we will use into our actors and will be exposed, that are the pre-start, that is executed every time our actor is spawned, so before starting its current behavior. There is the receive method that is called every time a message is received by the actor itself. The post-stop method that will be called every time the actor is killed. So mapping the life cycle of our actor. I go through this very basic example, really straightforward, just almost copy-pasting what is in the documentation. And so I spawn my WebSocket server through HTTP and whatever. And at the very end, when we start doing real things with it, so we have to listen. And when we have a request, when every time our WebSocket server will receive a request, it simply spawn a new actor that will handle the channel, as we already said. And this is completely easy. I said that one property of actors is spawning childs, and I mapped the action, the callback of receiving a request to the simple action of spawning a new child, with as argument the connection itself. And yes, second element with the WebSocket channel will be straightforward again, because it will be like a tube where messages are coming through and forth from the client to the Twitter service. So during the pre-start, we simply spawn the Twitter actor that will be a son of us. And every time from the WebSocket, we receive a message. We assume it is a message with a string that is a topic to track for the Twitter actor, and we forward pipe it to the Twitter actor. And when the connection gets closed, we simply kill ourselves. Killing ourselves means that when the actor dies, all his children gets killed consequently. And the receive message, that is when this WebSocket channel will receive a message, will simply forward it along the channel. That is the WebSocket. This is a really reusable piece of code, and this is something that you can use in different places. The point is that we are abstracting from the WebSocket implementation, and we are abstracting a little bit from the son that is Twitter. We are just building a pipe to make them communicate easily, one-to-one with the client. At this point, we have the Twitter service. The Twitter service, again, I don't know nothing about NPM, so I Google Node tweet stream, and there is a library. And again, I go down to the example, and what I can do is to track some topics, and I will receive a callback that is on tweet, and during the callback, I will receive the tweet itself. Let's do it. Let's use it for our Twitter service, our Twitter actor, indeed. And our Twitter actor, again, will spawn the Twitter module with the credentials during the pre-start phase, and it will map the callback that we have, that is about the tweet, to the action of sending to the parent, that is the channel, the stringified tweet in this case. And during the post-stop phase will be easy. We are just cleaning up resources. We are untracking things. And when we receive a message, and we are the Twitter actor, we are just going to call our module, our module to track effectively the message from Twitter. You can see that things are really encapsulated. So we don't have private fields here, but Twitter module is really private for this class. And we are not exposing it outside. The interface for and to this actor is just through sending and receiving messages. Again, everything is really modularized and is easy to test and is easy to put in one single place. And we can test, for example, this Twitter actor, so we can check that the connection is working. And we have just to spawn a new actor that will simply spawn by himself a new Twitter actor, track the topic pizza, and simply console log the messages that he will receive. To do that, we need a system. This is just a technical detail. Basically, every actor is spawned with, at the very top level, is spawned within an actor system. So an actor system is just a container for a number of your user actors. We can try to run this. And as you can see, it's all JavaScript. We are running on Node. And I forgot to save the file. And we can check if Twitter. OK, good. Yes, we are receiving tweets, and we are showing it outside, and this is on Node, and we are happy. It was a Scala library. It is running on Node, and we are not seeing anything about Scala. Easy peasy. All done. We have our server already implemented. You can look, that is 80 lines of code, right? And what we have learned, we have concept separation. Every element in our server that we have think about is a separate actor. We have just simply to implement a class for him to separate the concept from the rest. And we got away from the callback L directly, because we are mapping each callback to an action with vectors. And if you look at the documentation of this server, for example, you can see that things are starting to start to get nested and nested as you go on messages, etc. Instead, we are simply spawning a new WebSocket channel here. And the WebSocket channel is handling its very own callbacks. And each callback is mapped to an action, to directly an action. Is even no more is syntactically, and also the class is containing the code itself that is performing these actions. So it is kind of private for it, and we are getting away from this callback L. And we have free concurrency isolation. All of this is running concurrently. And we don't have to, for example, loop over connections within our server. We have everything that is really in a container, really separated. Concepts are really separated, and they are running concurrently. And it's 80 lines of code, so trivial. Just an exercise. Second part. we go for the front end, we have to show something to the user. We start trying to formalize a little bit our implementation, because on the front end, what you used to do during the implementation of implementing a system with vector model is to define the protocol. So you define in one file or in one section of your code all the messages that are going to and from your vectors. So you have a clear interface of what will happen in your vector system. In this case, we map one track class and one tweet class. We need to have a WebSocket actor that will be complementary to the other that we have seen on the server side that will handle the WebSocket themselves. So it will be an actor again, and it will take an argument that is the address, and in this case, during the press start, it will open the WebSocket connection to the server. We will map the action of onOpen on changing the behavior of the actor itself to be operative. So the default behavior is the receive, as I already said, and it is just simply logging that it is not ready, whatever you receive. But after the WebSocket is opened, you have to call the you have to think that the operative method will be called again, and every time you receive an instance of track, you will send it through the WebSocket, and every time you receive another message, you simply parse it from JSON because it was serialized on the WebSocket, and you send it to your parent. Again, we are just building a pipe for our WebSocket. We are abstracting from it. And on message, every time we receive a message, of course, we are redirecting it to ourselves. That is here. We are handling the parsing of the JSON. Now, we are at the point where we have to show something to the user. So Akka is intended to be a backend framework for just handling actors and with really good principles to me. But what we have, the next step is to bind things to the DOM. And there is no such a thing, but from now, and this is the very first time that I talk about it, and there is Akka.JS DOM. That is a library that I've developed on top of Akka, starting from the very basic principles of the actor model, and that enable you to use vector model to define even your UIs. And let me explain that I have, with really a simple implementation, I have for free, almost for free, a few really great advantages. But there is managing the local mutable state. It means that, to be honest, I started developing Akka.JS DOM having an interface to React, because React is so popular. But when I started, I felt dirty, really, because what React and all these kind of new frameworks are doing is taking the wall page, diffing on the wall page, managing all your state in one really global place on the top that is then flowing down to your functional approach, but everything is in a couple of places really global, really mutable, and really strange to me. It feels really bad to implement it with vector model. So what I implied is, what I started to think about is to map the life cycle of an actor to the life of a piece of DOM in your page. In this way, you can have a local mutable state managed within your actors. You don't track the whole page. Each actor is responsible for himself, and is responsible for the very small piece that he is managing. I just have to send in page the diff of what I'm changing from myself within the actor and apply it to the DOM. In this way, I'm using the virtual DOM to have performant algorithms to manage the patches, but they are run on a really, really small piece of HTML and DOM. We have, for free, page and application separation. Akka can be a quite heavy framework, and I don't want to load it into the page. So I think about a model where you can spawn, you can use your actors from outside the page. And since we have location transparency for application, our application can be used from workers, shared workers, or even from within the page, normally for debugging purposes. And then you send to a worker all the job to be done. We are leveraging a real parallelism, and everything is fully asynchronous, of course. But let's see how it looks like. First of all, we have to design a track input. So we have an input. We can write inside something, and pressing enter, we send a track message to the backend. This is our abstraction, is this DOM actor. It has a few methods more than a normal actor. Especially, you can see this render, that is the piece of DOM that will be rendered and will be managed by this actor on the page. And it's just an input. It will receive a WebSocket to communicate with the backend, and I will manage the events binding on these very small elements, the key up event, with a function that will basically return just the value of our input. When this actor receives a message, because every time an event is called, this function that is here, getTrackValue, is called, it returns a value. And it is sent to the actor back as a message. We don't have any insight on the implementation of the actor. You just receive a message. So when I receive a message from an event that is triggered in the page, I just receive it here, and I send a track with the value that it was written in the input to our backend through the WebSocket. Next thing I have to design is our Twitter UI, and this will show the message that we will receive from the backend. In this case, since we have a DOM actor, pre-start and post-stop are taken by the implementation of DOM actor itself, and we have to use post-mount. In this case, there is also post and mount that are really equivalent, but binded to the DOM. So this event is triggered after the element is really mounted on the DOM. And after this, we spawn a WebSocket, and we spawn a track input. Basically, again, we have a hierarchy. We are spawning a piece of DOM, and its son will be the track input, so even the visualization and is mapped to the life cycle of this little hierarchy. And we have the render that will simply show the tweet that we'll receive with simply some default value. And when he receives a message, I just trigger this internal function that is to update my DOM visualization. As we did before, we have simply to spawn our Twitter UI actor, and since the Twitter UI actor will spawn the WebSocket actor and the track input, all is done. And let me go to the results. Yes, I forgot to say that this will be called by the main, that is the only element that is loaded by the page itself. The page itself is pretty easy. It has just an element to bind my actor to, and the main use this UI manager that can take 3 types of elements that is one module, a worker, or a shared worker. In this way, you are free to, for production, to use your piece of code that uses DOM actor from wherever, with the location transparency feature implemented. And let's look at how it looks like. We have two elements that are spawned. As you can see, I can reuse this module at any time because they are simply mounted into the page, and this is how it looks like, the result. And let me start the server. Okay, and yes. And I'm connected to Twitter. Everything is concurrent. Everything is managed in page. Everything for free. What we have learned doing this, we have used the very, very same programming model. When I used to do backend and front-end development, usually you have to switch your mind. Okay, I'm doing backend. I have to think in this way. Now I have to do front-end. I have to use Angular. Everything changed. I have to use Redux. I have to use React. Whatever. You have to completely change your mind, think in the way your framework is told you to think, completely change your model. You hardly can reuse things from front to backend. In this case, everything is an actor. All the same, all the behaviors are reusable. Not only the objects, not only the properties, even the behaviors are reusable from front to backend. Imagine to write algorithms that uses concurrency, Raft, whatever. And you can reuse this code from front to backend freely. Reusability, of course, and multi-thread in 100 line of code, because you have, again, to see that our Twitter, yes, this is just a detail, is less than 100 line of code. And yes, I said multi-thread. I can show you. This is going to be fun. Our main is basically a playground. I implemented in the very same Prime UI. So a small piece of code that is reusable in page, and all the rest that is calculating prime numbers. And this, of course, won't work in a page, as you already know. And now I want to spawn 10 of them. I want to spawn 10 of them, and npm run build. Let's see what happened. So you can see that this is quite performant machine. I have 8 cores here. And reload this page. Okay, wait. No, it's just loading. This is just my browser. And you can see that around I have a number of get primes, and this will affect, of course, performances. But let's start with one. You can see that one CPU should go at 100. Now 2, 3, 4, 5, 6, 8, 9. More than my CPUs. Okay, this will fly, And now you think, okay, but my interface will be completely freezed by my computer having 8 cores at 100%. Let's see. Ah, no, it is working. Wow, like a charm. And I'm not lying. I can show you what happened. I have said to you that you can spawn your pieces of code even in page using the require, right? So let's spawn in page one prime calculator and see what happened in the page. This is given specially for debugging purposes because I missed something. Ah, come on, one blank line. Linters. I can say linters and no ID integration. You can see that much before everything else, I got this guy displayed in page because it is loaded in page within the thread of the page. So it is loaded first. You can use it even for gradual apps. If you want to show something really easy in the page, you can simply load it within the page. That will be the loading button or the waiting circle, whatever. And you can load it in the page. And now let's take my htop here. I trigger again all my CPUs to work. And now, let's do it. Look. You can see that everything, even I have difficulties to write here because our page is busy. It's busy trying to calculate prime numbers. And yes, it works, but come on, this won't be the way. No, this is just for showing you that really everything is asynchronous and everything is loaded outside from the page. Okay, let my laptop relax a little bit. If it can. Okay, kill it. Okay, I think I'm perfectly on time, so really time to take questions. And thank you so much for being here. And remember, you can help. This is the project. Go there, go to GitHub, participate. There is a lot of work to be done yet, so please come and enjoy it. Yes?
I'm surprised to see the cores are all being used. What is splitting out the work against the cores? Is it the browser that's allocated?
No, it's the operating system. So basically, every time you spawn a worker, it is spawned in a node VM, in a new node VM. So basically, I have my operating system that is scheduling between my node VM instances to split the work, so I can have more than my core instances of Node that are spinning at 100. But it's Linux business. No questions?
Thank you for your talk and welcome to Casablanca, Morocco. It's a pleasure to have you here.
Pleasure.
My question is, you mentioned talking about Scala that is just being a black box, not being interfered. So how much of the work is done in Scala? And if I may also ask you, why not? Scala was not one of the routes you took to actually put together your project.
Actually, you have everything apart from the DOM part available in Scala already. So only the DOM bindings are, I have ported them to Scala.JS actually. I have done some work there, but they look nicer in JavaScript, to be honest, because they interact with web workers and with the JavaScript ecosystem a little nicer. And the point is that everything else basically is in Scala, to be honest. If you go to GitHub Akka.JS, you can see that Akka.JS is a pure Scala project, and Akka.JS bindings that is the root of the Akka.JS npm module is all JavaScript. Sorry, is all Scala again. Only the demo are written in JavaScript because they are interacting. And on the other side, we have Akka.JS DOM that is completely JavaScript in this case because it's just the DOM part of the work. And yeah.
On another part, I mean, what you mentioned of how the DOM is not well written and it's giving headaches to everybody, and you pointed so well, and it is a reality on all the applications we're trying to write. We're constantly hitting the performance of our application on some stuff that we have nothing to do with. It's just the way how the DOM is being handled, how it's being trying to be safe and multi-threaded. Does your project, could we use that also in, is that a path should we follow on writing our own applications? Is that, could we be inspired of that?
Yeah.
Is it robust enough?
I think so. Basically what Akka.JS DOM, our Akka.JS DOM is divided is the front end and the back end. The front end actually itself the page does not actually use Akka.JS at all. So it's just a receiver of events from workers or from modules, and while it receives events, it propagates them to the page. Normally it receives just serialized events, serialized diff to be applied to the DOM. And that's the only interconnection point that you need in the page. So your page is 50 kilobytes or something, really small. And all the heavy work is done in the backend. That is, in this case, for workers. And in this case, it is done using Akka because it's a natural approach using message passing from backend to front end and from within the application itself. That felt really natural for me to implement. But of course, you can start from this one and roll out your own framework freely. Yeah. If you want, I have still a couple of minutes. I can show you a couple of things. And yes, about Akka. This project, just in case, it's Akka. Really, I'm taking Akka source code, and I'm taking Akka source code at every release, and I'm releasing Akka.JS consequently. So you have all the features that are implementing them, and all the performance shortcuts that they are implementing in Akka available in Akka.JS, most of them, let's say. And I'm just maintaining the diff that enable Akka to run on JavaScript. It's everything is written in Akka itself. And I have a few things going on, and this is a benchmark that shows you also how JavaScript virtual machines are going really fast nowadays. On the JVM, I have a ping pong basic benchmark that is running in around 1 second. And in the very last versions, I hit little more than 2 seconds to run it on single thread on Node. And this is great. Because on JVM, you have multi-thread and you have everything, and you know, it's completely different. And I narrowed it down in the very last versions really a lot, working on performances, and I kindly have eliminated all the most evident bottlenecks. Still quite, let's say, my very last problem is set timeout and set immediate, but that's another story. And yeah, many other things that are going. Akka.JS DOM, remote will enable you to communicate from front to backend without having to write the interfaces, and this will be great. And persistence, you can serialize directly the state of your actors on Postgres on backend, on local storage, PouchDB on front end. Oh, will be great. Many things going on. Okay, I'm done. Thank you so much.